Right, good morning, Year 10. So what we're going to do today is we're going to finish off the work we have been doing on stopping distances, and we're going to be looking today at reaction times. And as I said, this one is quite complicated, so you're going to need a little bit of time with this. Okay, so today's title is reaction time, so you can start by putting that in your book. And by the end of today, all of you should be able to list the various factors that can affect a person's reaction time, although you should be familiar with what some of those are. Most investigate the effect of caffeine on a person's reaction time and evaluate the accuracy of your investigation. And a few of you should be able to distinguish between the effects of distraction compared to other factors, although that we might actually leave for today. We'll see how it goes though. Okay, so the reaction time of a driver can affect the thinking distance and therefore the stopping distance of a car. So let's think about that logically for a minute. So if there is something that is affecting your thinking distance, basically something affecting your ability to react, um, if say for example that slows your reaction time, then obviously that means you are going to go further. Hence your overall stopping distance is going to be affected by your reaction time because it affects your thinking distance. So here's a question for you. Why does it not affect the braking distance? Okay, so can you pause the tape now, write down that question, and then just have a think and write down your best answer, and then we'll go through it in a moment. Okay, so the key reason why your reaction time does not affect your braking distance is because your braking distance is the distance you cover while under a braking force. You have already pressed the brake pedal down and you are exerting a force onto the brake discs of the car. So if you're already doing that, your reaction time at this point is not going to affect your braking distance. So key thing here, this is a fact which you are going to need. Okay, typical human reactions range from 0.2 seconds to 0.9 seconds. So again, it's probably worth just circling that and having it in your book. So once again, can you pause the tape and do that quickly now, please? Okay, so the next thing, reaction time can be affected by drugs. Now, if the drug is a stimulant, it might well increase your reaction time. If it is known as a depressant, it will slow your reaction time because it slows down the way nerves actually work, hence slows your reaction time. Alcohol is also the key one of these drugs. It is a depressant, so it will slow your reaction times down, and therefore you are at more risk of having an accident. Age, your reactions tend to get slower as you age. Tiredness, if you are tired, obviously your reactions aren't quite as good. Obviously, there could also be a link to distractions in there, and also weather conditions. They may affect your reaction time. So, what we are going to do today is we're going to plan an experiment to calculate reaction time. And actually, this is one we can do in your home right now because the only thing you need is a ruler. It says modeling clay, but we don't actually need that. All you actually need is a ruler. So what you can do is you can familiarize yourself with the basis of the experiment. On page 68, there is the experiment that describes this reaction time. So what you can do is pause the tape now and have a quick look through page 68 in your revision guide. It'll explain to you how you are going to do this, and then I'll go through it with you as well. Okay, so the first thing you're going to do is you're going to draw up a table like this, and you're going to need to find a ruler. And what you are going to do is you're going to hold your hand out open with your thumb pointing up, and you're going to get someone to drop the ruler, and you're going to try and catch it. Now, it's important that you don't give them a countdown or anything like that. You just surprise them, drop it when you can, and you are going to catch it as quickly as you can. And the first time you're going to do this without any kind of substances in your body, so you can do that as a control. So if you drop it, let's just say for example it falls say 20 centimeters. Okay, now because we have to do the distance in meters, 27 would be 0.2 meters. Okay, let's just say for the next one, second time you try it, it fell, I don't know, 25 centimeters, so you'd be 0.25. 0.25. Okay, and so on and so on until you've done 5 repeats. Then it's simply a question of calculating your mean. Okay, then what you're going to do, again, it's going to be quite fun. You can have half a cup of coffee and you'll need to wait between 7 or 8 minutes. Okay, that will allow the caffeine to get into your system. And then what you can do is do the same experiment again. So hold your arm out straight with your palm open and your thumb up, and then ask someone to drop the ruler, and you need to try and catch it. Okay, and once again, you will see how far it falls. Okay, so what you will hopefully have by the end is your average distance for your control before you start, your average distance after you've had half a cup of coffee, tea, or if you've got some Red Bulls in the fridge or something like that, that's fine. Coke works quite well because it also contains caffeine. And then after 1 cup, okay, and you can see how that affects the distance that it fell. Okay, so what you can do is pause the tape now, and you can go off and do this experiment. So this would probably take you about 15-20 minutes to do this properly. And then when you come back, I will show you how we can use this information in order to calculate your reaction time, because that is where the somewhat complicated maths comes in. Okay, so give it a quick go, see how you get on, and I will speak to you in a few minutes. Okay, welcome back. So what we are going to do is we are going to try and find our reaction time to dropping the ruler. Okay, so firstly, what you need to do is copy down this equation. I'm going to explain to you exactly what this means as we go. Now, luckily for you, this is not one of the equations that you are expected to remember. This is one that you are given on your equation sheet when you sit your exam. Okay, so it's v squared minus u squared equals 2as. Okay, and I'll go through what that means. However, what we do need to do is combine it with an equation which we do need to remember. And the equation that we do need to remember is this one down here, which is velocity, or change in velocity, divided by time equals acceleration. Or if we rearrange it, change in velocity divided by acceleration equals time, or acceleration times time equals change in velocity. So we were trying to find our reaction time. Okay, so let's just circle that, because that is the thing that we are actually trying to find. And I want you to just remember that for a few minutes. Okay, so we're trying to find the time, our reaction time. Okay, so what is V? Okay, well, V is the velocity, the speed at which our ruler is falling. Okay, U is its initial velocity, its starting velocity. Now, to work that out, we actually just need a little bit of common sense, and I'll explain that in just a moment. 2 is just 2. A is acceleration, and hopefully you remember that because we're also going to use that in this equation. You can see that's also down there. And S is the distance. I know you think it should be D, but it's not, because D was already taken for density. So I'm going to work through this example with you. Okay, so firstly, what you need to do is have your calculators on standby. So firstly, what we need to do is, in order to work out the time, we need to know something. We need to know the velocity. Okay, however, we've got the ability to work out v squared. So let's start with that. So firstly, u squared is the, or u is the initial velocity. Now again, using our common sense. So we're holding a ruler, it's just there, it's not moving. So its initial velocity is 0 meters per second. Okay, 2 is just that, it's 2. Now this is the tricky one. We've got to try and think. Acceleration. Now, at what rate do objects accelerate when they fall? Okay, the rate at which they accelerate when they fall, sorry, I got a little bit muddled up there, is 9.8 meters per second squared. Now you should be familiar with that number. 9.8 is the strength of gravity in Earth. Okay, and this final one, the distance that it fell, well, an example would be, say, 20 centimeters. So let's just say we caught the ruler after it's fallen 20 centimeters. That'd be 0.2 meters. So we put that in there. Right. So v squared minus u squared equals 2as. So with a bit of thought, we've got some numbers. We've got s, because it's 0.2. We've got a, the acceleration, 9.8, because that's something we're expected to know. And we've actually got the initial velocity, 0, because common sense dictates that it wasn't moving. So if we rearrange the equation, what we would do is this. 2 times 9.8, a, times 0.2, which is s, add 0, which is our distance. That will give us the velocity squared, okay? The velocity squared. So let's start working through that. So just bring up this calculator. Oh, just clear my last sum. Okay, so in this case, what I would do, just move that over there, 2 times 9.8 times 0.2, and you don't even have to bother to add the 0, but you can if you want. Add 0 equals, right, 3.92. So therefore, 3.92 is our velocity squared. Okay, so what we would need to do is simply then square root that. So you need to find the square root button on your calculator. Okay, a little embarrassing. I seem to have deleted the square root button on my calculator. I'm just going to do it on my one at home. So 3.92, square root of 3.92 is 1.97. So the velocity is 1.97 meters per second. So that is basically how fast the ruler was falling as you caught it, if it traveled 20 centimeters. Okay, now once we've got that number, to work out our reaction time, it's actually quite simple. We put 1.97 into our velocity, because that is our change of velocity. It was going at 0, it started at 0, it then accelerated to 1.97 meters per second. So that's our change in velocity. The acceleration we know is 9.8, because it's the same as Earth's gravity. So this one we can do quite easily. Okay, so clear that and go 1.97 meters per second squared divided by the acceleration, which is 9.8, and our reaction time was 0.2 seconds. Okay, and so there we have our method for working out our reaction time. Okay, so as you can see, it's quite complicated. We had to use two equations. This is a tricky one because we had to use this one, which will be given in the exam. We then had to rearrange it here and then take what we'd learned from that, 1.97, and put it into another equation that we were expected to remember in order to calculate the time. Okay, so another one for you to quickly try. Let's try doing exactly the same thing, only this time we're going to see if it's with a slightly different value. Okay, so Jim caught a ruler within 30 centimeters. So let's say he caught it at 30 centimeters. What I'd like you to do now is work out Jim's reaction time. So using exactly the same method, give it a go. Pause the tape now, see if you can work it out, and then we'll go through it in a moment. Okay, so we know that v squared minus u squared equals 2as. And again, that's one of the equations that you were given. So we rearrange it to v squared equals 2as add u squared. Okay, now a couple of things we know. Once we've got v squared, we then need to square root the whole thing. Okay, so how do we actually go about doing this? Right, so 2 times 9.8, that's a, that's the acceleration, it's gravity, times 0.3, that's the distance that it fell, add 0 meters per second squared. Okay, now remember 0 because it was not moving when we first dropped it. Once you've got all that, that will give you v squared. Okay, and then once you've got v squared, you square root the whole thing, and that gives you the velocity, which in this case was 2.42 meters per second squared. So that's how fast the ruler was falling as Jim caught it, 2.42 meters per second squared. Once we know the end velocity, we can use this to work out the reaction time. Because all you then need to do is the change in velocity, so time equals the change in velocity, which we just worked out, divided by gravity, which we know is 9.8 in Earth, and it gives us a reaction time of 0.247 seconds. Okay? Okay, so this is for the higher paper. So what you are expected to do, sorry, it seems to have printed over what I've done here, but never mind. You know that v squared minus u squared equals 2as. So this is the example from earlier. So we know our final velocity was 1.97 meters per second. So obviously that's squared. We know acceleration is 9.8, and we know distance is 0.2. So from the last slide, we worked out that v squared was 3.92, and then we did the square root of that to work out the velocity, which was 1.97 meters per second. Let's say, though, we didn't know the acceleration or the distance. We do, but we can confirm these. Okay, so what we're going to do is we're going to do the sum backwards now, so that we can work out the acceleration and that we can work out the distance. So remember, our distance was 0.2 and our acceleration was 9.8. So we were looking to confirm these. So the first thing we do is let's just pull up our calculator again. Okay, so let's just say we wanted to confirm that the acceleration was indeed 9.8. Right, v squared. Okay, so let's do that. Now our velocity was 1.97, squared, there it is, minus, well, 0, because our starting velocity was 0. Okay, so that's just, we can just leave that as it is. And then divided by brackets 2 times the distance, which was 0.2, close brackets, equals 9.7. Okay, that's pretty close. Okay, it's a little bit off because I think my calculations here, but Earth's gravity is 9.8. We come out with 9.7. So if we rounded to two significant figures, actually it would be 9.8. Okay, so we've calculated, we've confirmed that the acceleration was essentially 9.8. Okay, let's try the other one. So we're trying to work out what this distance is. Now we know the distance is 0.2, but we should still be able to confirm that. So 1.97, again, velocity squared. So let's square that. There it is, 3.8809. Okay. I think that one is the reason I'm a little bit off, because I think actually it was a longer number. I've just rounded it. Okay, minus u squared, again, which is minus 0, so don't need to worry too much about that, divided by, open brackets, 2 times 9.8, close brackets, okay, and we get 0.19, again, which is essentially 0.2 if we round it to two significant figures. Okay, so we've confirmed that our numbers, if we do the equation backwards, are indeed 9.8 for the acceleration and 0.2 for the distance. Okay, so it might be worth having this in your book next to this equation. So this is the equation you'd be given in the exam. And then what you would do is v squared minus u squared divided by 2s equals a. And then v squared minus u squared divided by 2 times the acceleration, or 2a, equals s, the distance. Okay, so it might be worth having those in your book now. Okay, so just going back a moment to your experiment, what you can do now is you can work out what your reaction time was from your own mean result. Okay, so what you would need is, this is the distance that the ruler fell, the average distance that the ruler fell in here, here, and here. And this actually allows us to experiment. Say, does caffeine increase our reaction time? That's an actual experimental question we can ask. Okay, so the first thing you would do is this. Okay, so let's just create a new page. Oops, correct. create a new page. It's not letting me do it for some reason. That's weird. Okay, sorry about that. So we were here, and what we were going to do was test the hypothesis: does caffeine increase or reduce, or sorry, does caffeine reduce your reaction time? So what you would need to do is take your distance that the ruler fell before you caught it, which would be there, to your control after after half a cup of coffee or some other caffeine drink, and then after 1 cup. Okay, so in each case, you should have an average distance that it fell. What you would then do is, remember, it's v squared minus u squared equals 2as. So you know that the acceleration is 9.8. You know that the initial velocity is 0. So what you would do is you would do 2 times 9. So it would be easier if I was typing this. 0.8. In fact, actually, I will type it. Bear with me a moment. So you would do 2 times 9.8 times whatever the distance was. So I'm just going to once again use the example 0.2, which was 20 centimeters. Okay, and then if you want to add your u squared, which 0, it's always going to be 0 because the initial velocity is going to be 0. And then whatever that number is, okay, you then square root the whole thing. Okay, so whatever that answer is, you square root it, and that will give you the velocity. Then it is simply a question of putting that number into this triangle. Okay, so once again, it would be to work out your reaction time, you would do the velocity divided by the acceleration that we know, because it's going to be 9.8, equals time, your reaction time. And you can do that for your control after half a cup and after 1 cup. And from that, you should be able to work out, does caffeine affect your reaction time? Okay, so pause the tape once more and give that a quick go, please. Okay, so this question is also at the bottom of page 68 in your revision guide. So I would like you to have a go at this. As you can see, it's worth 5 marks. This is the main part. So again, this is essentially just putting into practice what we've done. So you have a distance that it fell, and you need to then think about how this would work. Okay, so give this one a quick go, please. And what I will do is I'll post up the answer on Wednesday's lesson. Okay, final problem for you now. Okay, so this is slightly different. Okay, we're going to have to use our initiative here. How much force would be applied to the brakes if a car with a mass of 1,000 kilograms was traveling at 15 meters per second, came to a stop in 50 meters? And then, how long would it take? Okay, so we need to think quite carefully about how we answer this question. Okay, so let's start by looking at the values that we've got. How much force would be applied to the brakes if a car with a mass of 1,000 kilograms is traveling at 15 meters per second? Now, we could use force equals mass times acceleration. We certainly do have the mass. Okay, so let's just write that in. We've got the mass, 1,000 kilograms. So we'll just stick that under there for now. Okay, do we have the acceleration? No, we don't. So therefore, at the moment, we can't work out what the force is. Okay, let's see what else we've got to work with. Now, we could possibly work out the acceleration if we know the velocity or the change in velocity and the time. Okay, now this is where it starts getting a little bit tricky. Okay, now, do we have the change in velocity? Well, a car was travelling at 15 meters per second and it came to a stop. Right, so it was going 15, it's now come to a stop, which is 0, so its change is 15 meters per second. Okay, so we can put that change in there, and that's fine. Okay, so we know what that is now. But nowhere in here does it say anything about acceleration. Okay, so we're a little bit stuck at the moment, all right? So is there another equation which we could use? I think, what other ways could we calculate force? Okay, well, the main way, the other way we could calculate force is with this equation. Hopefully some of you remember this one, okay? Work done is force times distance. Now, I've been sneaky here. Do we have the distance? Yes, we do. We travelled 50 meters. Okay, there's our 50 meters. Okay, so at the moment we're a little bit stuck because we've got one value for each of our triangles, but we need at least 2 in one of these triangles to be able to work things out. So once again, we're a little bit stuck. Now, we need to think logically that we can work this out. Work done is what? Well, work done is the transfer of energy, okay? So let's think about that for a moment. Energy. How do we calculate energy? Is there any other way we can calculate energy? Well, sports fans, there is. So let's just get rid of this and I will reveal that. The work, energy transferred to stop the car, will be equal to the kinetic energy of the car. Because remember, energy can't be created or destroyed, only transferred. So the kinetic energy of the car will be transferred to heat, but it's still work being done. Okay, so to calculate the kinetic energy of the car, it's half mv squared. Okay, so that will give us the kinetic energy of the car, but that is also going to be the same as the work done. So let's just put that into a calculator. Let's just clear the last one. So half, which then is 0.5, times the mass, well, we know that was 1,000, times the velocity squared. Now the car was going at 15, so we do that squared, and that gives us 112,500 joules. Okay, so let's just type that in. 112,500. Okay, so now we do have 2 values. So what we can do is we can do that divided by that, and we've got our force. Okay, so quite simply, we do 112,500 divided by 50, and our force is 2,250 newtons. Excellent. Right, so let's start by putting that in. 2,250. There. Okay, now the first question was, how much force would be applied to the brakes if a car with a mass of 1,000 kilograms is travelling? Okay, at 50 meters per second and came to a stop in 50 meters. Right, we've got our force. But we can also now apply that to this. So we've got our force and we've got our mass. We can now work out the acceleration, or because it was slowing down, the negative acceleration. So once again, we take our force and divide it by the mass of the car, which was 1,000, and our acceleration would be 2.25. Actually, it'd be negative 2.25 because it's slowing down. Okay, so our acceleration would be that. And look at that. We've also can put that in down there. Okay, so we've simply plug that in there, and we can now do 15, which is our change in velocity, divided by our acceleration, 2.25. and we can see how long it took. So clear that. 15 divided by 2.25 equals 6.6 seconds. So that was how long it took to stop. Okay, so this was a significantly difficult question. You can see what I've had to do here. I started off by populating my equation triangles with the values that I did know. And then I had to think, right, how else can I calculate force? And I had to do it in quite an unconventional way. I had to go with work done, because work done is equal to the amount of kinetic energy. The work done on the brakes is equal to the kinetic energy that the car had. So there's the equation for kinetic energy, and I had everything I needed for that. I had the mass, 1,000, and I had the velocity, which I just needed to square, 15. So I did have everything I needed, but this would be an example of a typical challenge question that might come up in Physics 2. Okay, this would be probably a 6 to 8 marker. This would be the one you'd get right at the very end, which is a very, very high challenge question. Okay, but you can see that it can be done with just a little bit of logic and a little bit of work. So if you are sitting the higher paper you're aiming to, probably just quickly worth writing that down so that you know how to calculate this kind of question. Okay, I believe that's everything for today. So I hope you enjoyed doing the coffee and the ruler drop experiment. One last thing, it is 100% worth making sure you have a copy of the method on page 68. So your final task is to make sure you have a copy of the method on page 68 in your revision guide of how you do this experiment. Okay, so it's just 5 points in there. Okay, year 10, well done, and thank you.